Heat is not supposed to exist inside stone, yet certain crystals display colors so intense, the human eye instinctively associates them with combustion. Deep orange wavelengths rarely stabilize in nature without shifting toward red or fading toward yellow, which makes the appearance of sustained flame-like color inside solid crystal unusually difficult to explain at first glance. Some of these gemstones were overlooked for decades because their intensity only reveals itself under precise lighting. Others exist within chemical balances so narrow, even slight variations in trace elements would prevent the color from forming at all. And one occupies a compositional position so uncommon. Its optical character appears almost contradictory to how crystal chemistry typically behaves. These are not simply orange gemstones, they are instances where structure, chemistry, and probability converge within extremely limited margins. Moments where solid matter begins to resemble contained heat, starting with a gemstone whose quiet glow resembles the final stage of a burning ember. Ranked 10th, fire opal, the ember that looks like it's still burning. Not all fire appears as flame. Some forms of heat seem quieter, almost suspended, as if the moment of ignition never fully ended. Fire opal is one of the few gemstones that can create that impression. At first glance, the color appears simple, a warm orange body tone, sometimes translucent, sometimes softly clouded. Nothing about the structure suggests movement, intensity, or optical complexity. Yet, under directional light, the surface begins to behave differently than expected. Instead of reflecting sharp flashes, the color appears to deepen inward. Light does not simply bounce off the exterior facets, it seems to enter slow and settle within the material itself. This creates an unusual visual effect, not the sparkle associated with diamond and not the shifting rainbow phenomenon seen in traditional opal varieties. The appearance is closer to something more elemental, like looking into a fragment of material that has retained warmth long after the surrounding environment has cooled. Part of this impression comes from the internal structure of hydrated silica, which allows light to diffuse gently rather than reflect abruptly. The boundaries between illumination and shadow appear softened. Instead of high contrast flashes, fire opal produces a quiet saturation, a color that feels present even when the light source changes. Under warmer lighting conditions, the effect becomes more pronounced. The orange tone moves toward deep amber, sometimes approaching the visual threshold associated with heated metal or distant embers in low light. It becomes easier to understand why early traders often categorize these stones based on appearance alone, long before mineralogical distinctions were clearly defined. Unlike highly dispersive gemstones, fire opal rarely relies on brilliance to create visual interest. Its impact comes from persistence of color, the sense that the tone does not fade quickly as viewing angles shift. In controlled environments, this stability creates an unusual psychological response. Instead of chasing flashes of light, the eye remains fixed on the body color itself. There is a subtle tension created when a mineral surface appears to hold warmth, especially when the surrounding context suggests it should not. Because unlike molten material, this structure is entirely solid and entirely stable. Fire opal does not attempt to simulate flame through movement, it suggests something more restrained, the impression that the burning stage has already passed, yet the heat never fully disappeared, which raises a deeper question. If a gemstone can appear warm without emitting light, what happens when crystal chemistry begins to amplify the intensity of that color, beyond what the eye expects from natural formation? Because some orange gemstones do not simply resemble embers, some begin to resemble something closer to liquid fire. And the transition between those two states is where things become far less predictable. Number 9 reveals how light itself can hide intensity, until the exact moment it becomes visible. Ranked 9th, orange zircon, the flame that appears only when light finds it. Intensity is not always obvious at first glance. Certain materials appear visually calm, almost restrained, until illumination shifts slightly and reveals a completely different behavior beneath the surface. Orange zircon belongs to that category. In neutral lighting conditions, the color may appear stable, a refined orange tone with subtle brown undertones, sometimes mistaken for a less dynamic gemstone due to its relatively traditional crystal appearance. But the structure of zircon tells a different story. With one of the highest refractive indices among naturally occurring transparent gemstones, zircon interacts with light in a way that can produce surprisingly strong internal return. The effect does not always present itself immediately. Instead, it emerges gradually as the viewing angle changes. When light enters the crystal at the right orientation, internal reflections begin to separate and recombine in a way that intensifies the perceived warmth of the stone. Small flashes appear, not chaotic, but deliberate, brief signals of brightness that seem to ignite momentarily before disappearing again. Unlike gemstones known for continuous sparkle, zircon's optical performance often feels intermittent, as if the material reveals its full intensity only under very specific conditions. This intermittent behavior can lead to misjudgment. Collectors unfamiliar with zircon's optical potential sometimes overlook specimens whose true performance requires controlled lighting to fully appreciate. Under magnification, the crystal structure often displays a precision that supports this phenomenon. Light pathways remain coherent as they travel through the lattice, allowing distinct reflections to form without excessive diffusion. As a result, the color appears to activate rather than simply exist. Warm tones intensify briefly, producing flashes that resemble small points of ignition within the crystal. Not constant fire, but contained bursts, moments where the material appears to approach the visual energy associated with heated substances. Historically, zircon has experienced periods of under-recognition due to name confusion with synthetic cubic zirconia, despite the natural mineral predating modern simulants by centuries. Yet, when examined purely through the lens of optical physics, zircon demonstrates characteristics capable of producing a uniquely controlled form of brilliance. The flame is not obvious at all times, but when the alignment is correct, the response is immediate. A reminder that intensity does not always need to be continuous to be convincing. Sometimes the most compelling visual experiences occur when light reveals something that appeared hidden only seconds before. And if brief flashes of fire can already emerge from a relatively traditional crystal structure, the question becomes, what happens when saturation increases to the point where light no longer appears to reflect, but begins to look as though it is moving? Because further along this spectrum of orange gemstones, color does not simply glow. It begins to flow. Number 8 introduces a gemstone whose internal intensity creates the illusion of liquid heat suspended in crystal form. Ranked 8th, Mandarin garnet, when color becomes liquid. Some gemstones reflect light, others appear to contain it. Mandarin garnet occupies a visual category that often feels less like reflection and more like suspension, as though color itself has taken on physical presence inside the crystal. Unlike lighter orange minerals that rely on transparency to create brightness, Mandarin garnet develops intensity through saturation. The concentration of manganese within the garnet structure produces an orange tone so rich that the boundaries between light and material begin to blur. Instead of observing flashes that appear and disappear, the eye encounters something more continuous, a sense that the interior of the gemstone is filled with moving warmth. Under focused illumination, the color does not simply brighten, it thickens. The orange deepens toward a tone reminiscent of heated resin or molten glass at the moment it begins to glow but has not yet reached transparency. The effect can feel unusually cohesive, as if the internal environment of the crystal maintains consistent visual temperature regardless of minor changes in viewing angle. This consistency distinguishes Mandarin garnet from many other orange gemstones. Rather than relying on contrast between light and dark zones, the crystal often presents a nearly uninterrupted field of color. Such uniform saturation allows subtle variations in internal structure to guide light smoothly through the material, producing a sensation that appears less like sparkle and more like flow. In certain specimens, the internal reflections appear soft at the edges without sharp interruptions. Light transitions gradually between zones of intensity, creating the impression that illumination is traveling through a dense medium rather than bouncing between rigid surfaces. This is where perception begins to shift. When brightness behaves as though it has viscosity, the mind no longer interprets the stone as static matter. It begins to interpret the experience as motion, even though the crystal remains completely still. Gemologically, this effect can be attributed to the combination of refractive index, transparency balance, and chromophore concentration that defines the Mandarin variety of sphalerite garnet. But scientifically accurate explanations do not diminish the visual impression. If anything, they reinforce how unusual the outcome truly is. Color rarely appears this stable at such intensity without shifting toward red or losing clarity through internal scattering. Yet Mandarin garnet maintains equilibrium between depth and brightness, a narrow optical window that few minerals achieve naturally. Because once color density reaches this level, the risk of opacity typically increases. Instead, the internal glow remains active, almost cohesive, almost fluid. And when color begins to behave like a substance rather than a surface property, the distinction between heated material and solid crystal becomes increasingly difficult to define visually. Still, saturation alone does not explain how certain orange gemstones acquire tones that appear hotter than their formation environment would normally allow. Because deeper in the geological record, there exist minerals whose very presence challenges assumptions about which thermal conditions are required to produce colors associated with extreme heat. Number 7 reveals a gemstone whose color resembles material exposed to temperatures far beyond what its crystal structure should logically suggest. Ranked 7th, Clinohumite, the color that suggests more heat than nature should allow. Temperature leaves visual signatures. Metal begins to glow at specific thresholds. Ceramics change appearance as thermal energy alters their internal structure. Even in darkness, certain materials carry subtle chromatic cues that suggest exposure to extreme conditions. Clinohumite displays a similar visual suggestion, a deep orange tone that often resembles substances shaped by sustained heat. Yet the environments responsible for forming gem-quality clinohumite do not always align with the temperatures implied by its appearance. This contrast is what makes the stone particularly intriguing. The color frequently leans toward a dense orange-brown spectrum associated with refractory materials, compounds engineered to withstand high thermal stress. The resemblance can create an intuitive assumption that such coloration must originate from exceptionally intense geological heat. However, clinohumite forms within metamorphic environments where pressure and chemical composition interact in precise balance. The presence of fluorine within the mineral structure plays a significant role in stabilizing the crystal lattice, allowing color centers to develop under conditions that are more complex than simply high temperature alone. Trace elements influence absorption patterns within the visible spectrum, shaping how wavelengths interact with the crystal. The result is a color that visually suggests thermal intensity beyond what observers typically associate with gem formation. Unlike transparent orange gemstones that rely on light return to create brilliance, clinohumite often expresses its character through density of tone. The color appears grounded, substantial, as though the material has undergone transformation through forces capable of altering its internal equilibrium. When illuminated under neutral lighting, the surface does not immediately reveal strong reflections. Instead, the hue gradually emerges with depth, producing a stable impression that feels resistant to rapid visual change. This stability contributes to the perception that the stone contains a history of pressure and thermal influence embedded within its structure. Not because the temperature was extreme in isolation, but because multiple geological variables converged in a narrow window of formation, conditions rarely achieved in combination. Gem-quality clinohumite remains uncommon precisely because the balance required for crystal clarity does not frequently occur alongside the chemical environment necessary to produce its distinctive coloration. Too little fluorine and the structure shifts. Too much alteration and transparency is compromised. The margin between viable crystal growth and structural instability remains remarkably small. Such constraints help explain why certain orange gemstones appear visually aligned with high-energy processes rarely preserved in stable crystalline form, because the color itself can imply exposure to forces that the mineral record does not always preserve in predictable ways. And when appearance begins to challenge expectation, perception shifts from simple appreciation toward analytical curiosity. If one mineral can suggest temperatures beyond what its formation environment might imply, what happens when chemistry restricts color expression even further? Because achieving a truly balanced orange, without drifting toward red or yellow, requires an even narrower alignment of atomic influences. Number 6 explores why producing a pure orange gemstone may be far more difficult than the color itself initially suggests. Ranked 6th, orange sapphire, the narrow spectrum where fire can exist. Color rarely settles exactly where expectation places it. Within the visible spectrum, orange occupies a remarkably unstable position, balanced between the dominance of red wavelengths and the brightness of yellow light. Even minor variations in trace element concentration can shift the appearance noticeably in one direction or the other. For most minerals, achieving a stable orange tone is not the natural outcome. It is the exception. Corundum, the mineral species responsible for sapphire, demonstrates this challenge with particular clarity. While the crystal structure of corundum is capable of producing a wide range of colors through trace element substitution, the pathway toward a distinctly orange result requires a precise combination of chromophores interacting within an extremely limited tolerance. Iron, chromium, and occasionally other trace elements must align in ratios that neither overpower the structure with red saturation nor dilute the color toward yellow transparency. If the balance moves too far toward chromium influence, the visual result approaches ruby-like tones. If iron dominates excessively, the color may appear muted or shift toward golden hues that no longer resemble flame intensity. Between these two tendencies lies a narrow optical interval where orange can exist with clarity and stability. This interval is far smaller than many observers expect. Under controlled lighting, fine orange sapphire specimens often display a warmth that feels distinctly different from surrounding color families. The tone appears neither aggressive nor pale. Instead, the saturation suggests equilibrium, a visual midpoint that allows the eye to perceive depth without overwhelming brightness. Because the human visual system interprets orange as a transitional color, slight deviations become highly noticeable. Stones that fall just outside the optimal balance may still appear attractive, but they no longer create the impression associated with contained heat. The most compelling examples maintain a chromatic steadiness that feels internally consistent across multiple lighting environments. This stability becomes increasingly difficult to achieve as crystal growth conditions vary. Temperature, pressure, and chemical availability must align over sufficient time to allow trace elements to distribute evenly within the lattice. Rapid shifts in formation environment often disrupt this equilibrium, resulting in color zoning or mixed spectral influences that prevent the stone from maintaining a cohesive orange identity. Such constraints help explain why distinctly orange sapphire remains relatively uncommon compared to other color varieties within the corundum family. The challenge is not that orange cannot form. It is that the structure rarely allows it to persist without interference from adjacent spectral influences. When successful, the result produces a visual temperature that appears balanced rather than extreme, not the intensity of open flame, but the steady presence of sustained heat, a color that suggests controlled energy rather than combustion. Understanding how narrow this chromatic window truly is begins to shift perception. Because rarity does not always arise from dramatic geological events. Sometimes it emerges from the difficulty of maintaining stability within a system naturally inclined toward imbalance. And once collectors begin recognizing how uncommon this equilibrium can be, attention tends to follow accordingly. Number 5 marks the point where perception of orange gemstones began to change, not because the minerals themselves transformed, but because observers started noticing the fire that had always been present. Ranked 5th, Imperial topaz. When perception finally recognized the flame. Market attention does not always follow optical performance. Certain gemstones remain outside mainstream focus for extended periods, not because their visual properties lack intensity, but because historical classification systems tend to prioritize more familiar color narratives. Imperial topaz illustrates how perception can delay recognition of optical character that was always present within the material. For much of gemological history, emphasis concentrated heavily on saturated reds and deep blues, colors traditionally associated with rarity, status, and durability in cultural symbolism. Orange tones often occupied an ambiguous space between these established categories, perceived as transitional rather than definitive. Yet imperial topaz demonstrates how transitional colors can produce visual effects that feel remarkably stable. The internal structure of topaz allows light to travel through the crystal with relatively low distortion, preserving clarity while supporting warm chromatic saturation. In fine orange specimens, trace elements create a coloration that appears neither diluted nor excessively intense, but balanced within a range that evokes steady thermal presence. Unlike stones that depend on dramatic brilliance, imperial topaz frequently expresses its character through controlled luminosity. Light does not scatter aggressively. Instead, illumination seems to gather gradually within the body of the crystal, building depth rather than contrast. This creates a visual continuity that resembles the stable glow associated with sustained combustion, not the unpredictable motion of flame, but the persistent radiance of material that has reached thermal equilibrium. Such optical behavior can be easily overlooked in environments where sparkle dominates aesthetic preference. However, as collectors increasingly examined gemstone performance under varied lighting conditions, appreciation began to expand beyond traditional color hierarchies. Orange stones capable of maintaining saturation without appearing opaque started to occupy a more defined position within curated collections. Imperial topaz, particularly specimens displaying rich orange tones without excessive brown influence, became a reference point for understanding how warmth can be conveyed through structure rather than surface brilliance. The perception shift did not occur abruptly. It developed gradually as comparative observation allowed subtle differences in color stability to become more apparent. Over time, the ability of certain orange gemstones to sustain visual warmth across multiple viewing environments began to carry greater significance. Not because the stones themselves changed, but because attention adapted. Recognition often follows familiarity, and familiarity frequently reveals complexity that initial observation may overlook. As more observers encountered the controlled glow present in well-formed orange topaz crystals, the assumption that orange represented a secondary color category became increasingly difficult to maintain. Because sustained visual warmth implies structural consistency, and structural consistency suggests an underlying mechanism guiding how light interacts with the lattice. Understanding that mechanism requires examining how crystal symmetry influences the amplification of heat-associated color wavelengths. Number 4 moves deeper into the structural framework responsible for intensifying orange coloration beyond what surface observation alone can explain. Ranked 4th, orange spinel, when crystal symmetry intensifies the appearance of heat. Structure determines behavior long before light ever reaches the surface. Within crystalline materials, atomic arrangement governs how energy moves, how wavelengths are absorbed, and how color ultimately presents itself to the observer. Even subtle variations in lattice symmetry can alter the visual outcome dramatically. Spinel provides a particularly revealing example of this principle. Unlike minerals whose internal arrangement produces directional color zoning, spinel's cubic crystal structure distributes optical response with remarkable uniformity. This symmetry allows light to interact with the lattice in a balanced manner, reducing irregularities that might otherwise disrupt the perception of consistent color intensity. In orange varieties of spinel, this structural equilibrium creates a visual effect that feels concentrated yet controlled. Rather than scattering unevenly, illumination remains coherent as it travels through the crystal. The result is a color presentation that appears stable across multiple viewing angles, reinforcing the impression that the warmth observed is inherent to the material itself rather than dependent on momentary reflection. Because the lattice does not favor one directional pathway over another, chromophore distribution can express itself more evenly throughout the crystal volume. Trace elements responsible for orange coloration remain optically integrated within the structure, minimizing abrupt transitions that might otherwise interrupt the continuity of perceived heat. This continuity becomes visually significant. When color intensity appears uninterrupted by structural inconsistencies, the mind interprets the material as internally energized rather than externally illuminated. The difference may appear subtle at first, yet the psychological effect is measurable. Uniform color stability often produces a stronger association with thermal presence than fragmented flashes of brilliance. Spinel's optical neutrality also contributes to its ability to maintain clarity while supporting saturated tones. In many gemstones, increasing color intensity risks introducing visual heaviness or reducing transparency. However, spinel frequently preserves internal openness even when chromatic saturation rises. This balance allows orange tones to remain vivid without appearing dense or opaque. The impression resembles material that continues to emit warmth without losing structural definition. Such behavior is particularly relevant when examining why certain orange gemstones appear more visually heated than others with similar color coordinates. It is not solely the wavelength that matters. It is how consistently that wavelength is expressed throughout the crystal volume. When structural symmetry supports uniform light interaction, the visual field stabilizes. Stability enhances perceived intensity, and perceived intensity reinforces the association between color and heat. Understanding this relationship reveals why certain orange stones produce a stronger thermal illusion even when measured chromatic values appear comparable to less visually compelling specimens, because the experience of color is influenced not only by chemistry, but by how structure preserves or disrupts optical continuity. Yet even the most stable crystal frameworks depend on geological environments capable of supplying the necessary trace elements in sufficiently narrow concentration ranges. Such conditions rarely occur uniformly across large regions of the Earth. Number 3 explores the geological constraints that make certain flame-like orange gemstones far less common than their visual familiarity might suggest. Ranked third, Bastnäsite. When rare earth elements create an uncommon flame. Geological rarity often begins long before crystal growth becomes visible. Certain color expressions depend not only on pressure and temperature, but on the presence of elements that themselves occur infrequently within the Earth's crust. When these components must converge within the same formation environment, probability narrows considerably. Bastnäsite forms under such constraints. As a rare earth fluorocarbonate mineral, its chemical composition includes elements such as cerium and lanthanum, components more commonly associated with advanced technological applications than with gemstones typically encountered in jewelry contexts. These rare earth elements influence how the crystal absorbs and transmits specific wavelengths of light, contributing to coloration that frequently falls within the orange spectrum. Yet the presence of color alone does not explain the perception of heat-like intensity. What distinguishes Bastnäsite is the limited number of geological settings capable of concentrating rare earth elements in sufficient quantities to support crystal development. Most geological environments disperse these elements too widely to allow visually coherent specimens to form. Even when chemical availability exists, additional structural requirements must still be satisfied. The crystal must develop with sufficient transparency to allow light interaction. The internal structure must remain stable enough to avoid fracturing during growth, and The trace element distribution must remain relatively uniform to prevent uneven color zoning. Each of these conditions introduces additional layers of improbability. When combined, the number of environments capable of producing visually compelling Bastnäsite specimens becomes significantly constrained. From an observational perspective, this limitation influences perception. When a color appears that the geological record produces only sparingly, the mind tends to interpret the visual signal differently. Scarcity alters expectation. Expectation alters attention. Orange tones generated through rare earth influence often display subtle differences in spectral behavior compared to more common chromophore systems. The result can appear slightly more concentrated, slightly more grounded, as though the color originates from a deeper structural level within the material. Because rare earth elements affect how energy transitions occur at the atomic scale, the resulting chromatic output may feel unusually cohesive, not brighter in a traditional sense, but more internally anchored. This anchored quality contributes to the impression that the color is not merely applied to the surface, but integrated throughout the mineral's identity. When geological probability restricts formation opportunities so tightly, even modest visual intensity can appear amplified by contextual rarity. Understanding how infrequently such elemental combinations align helps explain why certain flame-like orange gemstones are encountered far less often than casual observation might suggest. Because nature does not distribute the necessary ingredients evenly, it concentrates them selectively. And selective concentration introduces natural limits on repetition. Yet rarity alone does not fully account for the moments when orange gemstones appear so visually intense that observers question whether the coloration could occur without artificial influence. Number 2 examines a gemstone whose optical behavior becomes so vivid that its natural origin is sometimes questioned upon first encounter. Ranked second, Sphalerite, the orange crystal that produces sparks of light. At certain levels of optical intensity, visual behavior begins to challenge expectation. Most gemstones distribute light in ways the eye has learned to recognize. Reflections appear controlled, brilliance follows predictable patterns, and dispersion typically enhances beauty without disrupting realism. Sphalerite operates beyond that familiar range, possessing one of the highest dispersion values found in naturally occurring transparent minerals. Sphalerite separates white light into spectral components with unusual strength. This separation produces rapid flashes of color that appear sharply defined, often emerging in concentrated bursts rather than gradual transitions. When observed under directional lighting, these flashes can resemble momentary sparks suspended within the crystal. Brief points of spectral intensity appear and vanish as viewing angles shift, creating an impression of internal activation rather than surface reflection. Because dispersion influences how wavelengths travel at different velocities through the lattice, each rotation of the crystal alters the alignment of light pathways. The result is not continuous brilliance, but episodic ignition-like signals that feel visually energetic. In orange varieties of sphalerite, the warm body color enhances this perception further. Instead of dispersing into cooler hues that contrast strongly with the primary tone, many flashes remain within a chromatic range that reinforces the impression of heated material. Gold transitions toward amber. Amber deepens toward ember. Short intervals of brightness appear, concentrated enough to resemble tiny points of combustion occurring within solid matter. From a gemological perspective, sphalerite's optical behavior results from its high refractive index combined with unusually strong dispersion relative to many more widely recognized gemstones. However, explaining the mechanism does not fully diminish the visual surprise created when observing the effect directly. Because dispersion of this magnitude is rarely encountered in minerals typically associated with jewelry or collector specimens. Even under moderate illumination, sphalerite may display spectral separation strong enough to exceed intuitive expectations of how light should behave inside a transparent crystal. This contrast between expectation and observation contributes to the impression that the material is operating outside typical visual parameters, not brighter in a simple sense, but more dynamically responsive to small changes in viewing geometry. Each subtle adjustment introduces new flashes, new alignments, new moments where light appears to accelerate briefly before stabilizing again. Such responsiveness can create the illusion that energy is being released intermittently from within the structure, not continuously, but unpredictably. And unpredictability strengthens the association with ignition phenomena observed in heated substances transitioning between states. Despite this intense optical performance, sphalerite remains relatively unfamiliar to broader audiences, partly due to its lower hardness compared to more durable gemstones. Yet from a purely optical standpoint, the mineral demonstrates how crystal chemistry can produce visual intensity that rivals or exceeds far more commonly discussed species. Because when dispersion reaches sufficient magnitude, the boundary between reflection and perceived motion begins to blur. And when motion appears present within a solid crystal, interpretation often shifts toward the language of energy. If dispersion alone can create flashes resembling sparks, the final position must represent something even more unusual. Because one orange gemstone exists within a compositional space so narrowly defined that its very color appears statistically improbable. Number 1 reveals the crystal whose balance of chemistry and structure produces an orange tone that seems to exist between established definitions. In first place, Malaya garnet, the orange that exists between definitions. Malaya garnet occupies a position that complicates those boundaries. Rather than conforming neatly to a single compositional identity, this variety exists within an intermediate zone between pyrope and sphalerite garnet chemistry. The resulting mixture produces color outcomes that do not always align with expectations associated with either end-member species. In many cases, orange coloration emerges through transitional trace element influence, creating tones that appear balanced between red-dominant and yellow-dominant chromatic tendencies. Such equilibrium rarely persists without interference, because when multiple chromophore systems interact simultaneously, competition between absorption pathways often produces instability in perceived color output. Yet, certain Malaya garnet specimens achieve a surprising level of chromatic coherence. Instead of displaying mixed or muddled coloration, the crystal can present a distinctly warm orange tone that feels visually resolved despite its chemically intermediate nature. This coherence contributes to the perception that the color occupies a space not commonly represented within traditional gemstone classifications, not entirely aligned with established garnet expectations, not fully separable into alternative categories, positioned instead within a narrow compositional interval where color behavior appears unexpectedly refined. Optically, this refinement often produces saturation that suggests controlled internal energy rather than scattered chromatic influence. The orange tone can appear stabilized as though the crystal lattice has resolved competing elemental signals into a unified visual expression. Because pyrope components introduce depth of color while sphalerite influence contributes brightness, the resulting balance can create a warmth that feels structurally supported rather than visually incidental. Such structural support enhances the impression of contained intensity, not the unstable motion associated with open flame, but the steady radiance associated with material that has reached equilibrium within a confined energetic state. When examined alongside more compositionally straightforward orange gemstones, Malaya garnet often appears subtly different. The color does not necessarily appear stronger, but it appears more internally consistent across varying lighting environments. Consistency reinforces credibility. Credibility strengthens perception of authenticity, and authenticity allows unusual color behavior to be interpreted as natural rather than anomalous. From a geological perspective, the formation of such compositional balance requires specific elemental availability during crystal growth. Too little manganese influence, and the structure shifts toward deeper red. Too little pyrope contribution, and the resulting tone may lose depth. Maintaining this equilibrium across the entire crystal volume narrows the probability window significantly, because intermediate chemistry rarely produces stable color expression without visible compromise. Yet in rare instances, the balance holds. The resulting color occupies a position that appears both familiar and unexpected simultaneously, recognizable as orange, yet visually distinct from the typical outcomes associated with single-source chromophore systems. This duality contributes to the impression that the gemstone exists slightly outside conventional expectation, not because the mineral itself defies natural law, but because the pathway required to produce its color remains unusually precise, and precision within geological systems rarely produces repetition at scale. When considered collectively, orange gemstones reveal a pattern often overlooked in broader color hierarchies. The appearance of heat within crystal structures does not originate from temperature alone. It emerges from balance between chemistry and structure, between absorption and transmission, between rarity and recognition. What appears at first glance to resemble flame may in fact represent something more stable, a visual reminder that intensity in nature often arises from constraint rather than excess, and that certain colors only emerge when multiple unlikely conditions align without deviation. Under those circumstances, even solid crystal can appear to contain the quiet persistence of fire. Orange is one of the least stable colors in natural crystal formation. It exists within a narrow balance of chemistry, structure, and probability, a balance that rarely holds long enough to produce sustained intensity. What appears at first glance to resemble fire is often the result of extremely precise optical conditions preserved inside solid mineral structures. Not combustion, not illusion, but physics expressed through color. And once the eye begins to recognize how uncommon this balance truly is, many other gemstones begin to look different as well, because some of the most convincing visual effects in nature are not created by heat. They are created by structure.